to calculate the probability of choosing an action in FPL is unknown. Right? You cannot directly calculate that. And the reason you cannot directly calculate is because actually you're not sampling, but you are solving an underlying optimization problem. So what is the chance? What are the chances that your action is the optimal solution for the underlying optimization problem? It's very difficult to calculate that probability. Okay? And because of this, most people don't want to calculate. But there's a very recent paper from 2013 and then later journal version 2015 of Gerdenoy and Bartle, who actually managed to not to calculate the value, but to estimate the value. And the way is very simple. So you think about this underlying problem, to solve it. Your action is either a solution or not, right? You regenerate the underlying problem because you can change the random noise, and you resolve it again. You solve it second time. Is it a solution? No. Solve again. Is it a solution? Yes. No. Solve again. You solve it until it becomes a solution. And this is flipping a coin. Right? You flip a coin. You see it? No. Flip again. You see it? No. Flip again. You flip until you see it. And this is the geometric distribution, right? And what is the probability of seeing a solution? It's exactly the P, the one we want to calculate, which we don't know. So this is kind of the reverse engineering to calculate the probability of flipping that coin, of having our action as a solution without knowing what the probability is, by simulating. And you stop when you see it. Okay? And that sequence, the number of attempts, the number of trials, give you expected value of 1 over that probability. Right? This is classical geometric sampling. So the expectation of number of rounds you need to rerun, to resolve, is exactly 1 over P, the one we want to calculate. And it's very beautiful. Right? The idea behind it is again randomization. It's something you cannot control, make it randomize it, and then use the expectation. Yeah? So that's the trick behind this. Yeah, this is a paper, so they are papers, and this is our modification to make it even better. Good. Okay. So the theory behind this is that if we do all kind of tricks, actually we can prove that the regret now is square root of t, and also square root of the dimension as well. So everything, almost everything, is something here. Okay? So this is very good. So now we can achieve something there with that as well. Okay, so a very special case of this model is when it becomes stochastic again. So it's not adversarial combinatorial, but stochastic. Then in this case, you can modify the algorithm a little bit. You can not even a little bit. Actually, you can completely forget about FPL. You can do something like the UCB. You modify UCB. So see again, see this is something like the UCB type, right? But now instead of like you having one index, you do the indexing for each of the dimensions. Sum them up, and then you can prove the similar thing. Okay, so I'm going to go just high level now, but I hope that you understand the essence. So now the theory can be like this. So the regret is going to be the logarithmic of t. T is the time horizon. This is a little bit big, n is number of dimensions. But if you have small dimensions, there shouldn't be a problem. Okay. You can also have another version of this when instead of having a bandit or semi-bandit feedback, you see the whole function yourself. And things even better because in this case, actually now you don't need to do the trick like unbiased estimator, blah blah, because you see everything. Every round you see everything, right? So you have the value straight away. So things should be much better.
You just said that instead of like bandit feedback, here we see the whole function, or we see the value of the functions at every arm.
Yeah. And this is realistic because you can think there are lots of cases like think about like investment, financial investments, right? So you can that if you put million pounds into an investment, you get a return, something, right? If you put 20 million pounds, you can calculate this because you see that what happened with the stocks, right? You buy 10 stocks, you buy 10,000 stocks, you can calculate the things.
Okay.
Yeah? So you see the function. Okay? So that was the combinatorial bandit.
Any version with like kind of with budget, like instead of you can choose K arms, you just choose like subset of them.
Yeah, that's what my PhD thesis is.
Okay.
I'm going to talk about it later in afternoon. Just a little bit.
Okay.
So the next version of combinatorial bandits is linear bandits. So in combinatorial, we can choose more than one points, but there's still no correlation between them. Right? So the correlation happens at the function state, because it's a sum of the points we have chosen. So another version of this is linear bandits, where actually the correlation is within the arms. So we have some kind of matrix space here. So everything is still the same. Yeah. So the only difference is that now adversary he doesn't choose arbitrarily the point. Instead, he chooses one single vector. Okay, one single vector. And now the function is the dot product between our chosen vector and the opponent's vector. Okay. So now the correlation, you can see that it generates a matrix space. Because if I'm here and choose my point, then I see my value. Actually, I can estimate if I move a little bit away. Because if I move a little bit away in the space, then the value should move very far either. Right? Because it's still everything is in linear space. And the guy uses the same vector for the whole subspace. He can change his vector next round, but for this round, it's the same. So you can do nice things. You can estimate how far you would get if you move away from your chosen point, because everything is linear. So because of this trick, now you can do lots of nice things. For example, you can use X3 to calculate the next arm to 2, for example. Almost the same, so it doesn't have to. You don't need to see the details. But the only thing is that now that the uniform distribution is not on single points anymore, but single arms anymore, but over the whole space, whole linear space. This is something that could be practically challenging, because you have to implement how to sample how to uniform sample from a particular space. Okay.